To the issue of understanding perception and behavior. And before it's too late, I want to mention, you can read the list of people I'm collaborating with in this particular topic. And I don't think I'm going to talk about the things that we are doing with Siddhartha. You were supposed to talk about that. Diego probably will talk about that. So let me give you a bit of a pontification here. So I wanted to emphasize this idea of capturing the grandiose title of Thermodynamics of Perception and Behavior. I wanted to capture the idea that it's a personal realization that I had. I'm not the only one, but it's personal for me. That as physicists, as Siddhartha was saying, we really focus on a very reductionistic approach to brain science. And we love our neurons and our networks, and we work on that, and we try to come up with theories and new mathematics to model the complex behavior of neurons. But too often we forget about what really matters, what is the function of the brain, which is behavior, and perception is one of the elements of behavior, as Sergio was saying this morning. And it's interesting because we see now that there is a deluge of new techniques for recording neurons and neural tissue that is providing a huge amount of data. But it's also true for perception and behavior. We have an enormous amount of information being collected of human behavior from, the Fitbit devices that people are wearing. It's very common now to see that in New York. Everyone is crazy about fitness. And we have digitized books, millions and millions and billions of digitized books. We have voice recordings, we have video recordings, and that's almost on a par with, like I said, all this marvelous techniques that we have to do studies of neurons and groups of neurons. And also, as a physicist, this made me think about the relationship between statistical mechanics and thermodynamics, that to a large extent, we developed first thermodynamics. We developed first the idea of conceptualizing microscopic variables, and that led us to a much better understanding of how to go from the molecular foundations to the macroscopic description of the system. So clearly we had to walk along this line up and down in terms of understanding the brain. So what I wanted to do is tell you a little bit more about what is that we are doing along this axis of using massive information in some cases, massive data from behavior, in some other cases, just looking at behavior and trying to conceptualize it in the same way that you conceptualize anything in physics. And I'm wearing this device. I don't know how many of you are familiar with EEG. This is a one electrode EEG. It's Bluetooth. It's in the US it's $80. And I invite you to pass it around, and then I'll take this off, and you can play with it. What did you do? Don't touch the screen. Okay, it's coming. So yeah, you can pass it around. It has the app provides a couple of measures. One is a measure of attention. That one is a measure of meditation, but I have software that can record around 10 frequency bands in the EEG spectrum of this one electrode. And what we want to do for the course is for you to come up with a simple experimental design and use this software to record these bands and try to come up with a little theory or some way of analyzing the data that will make sense. And it's open-ended, of course, but I think it would be a very good experience because this will be real data. And I don't know if you can see it, but I should be able to turn on the attention right now. Okay? Okay. So how is the tension dial? Okay, it should be. Yeah, okay. I will not be talking about this specifically, but I wanted to show it as a token of what I'm trying to convey, which is the emergence of this massive amount of data of behavior and perception that we can and we should use because I think it's as important as understanding what's going on at the molecular level and the neuronal level, because the two levels are connected for the purpose of generating function. So let's see if I don't repeat Siddhartha's experience. I don't know how much I can cover, but I'll be talking first about modeling pain, and then I'll talk about work that we have done modeling music perception, again using large databases, and then work that we've been doing, in fact, with Diego, who's over there on chess, using massive online databases of chess games. And I will not talk about this, but it's something that maybe I'll just touch a little bit upon. That is the idea of using tools from physics and mathematics to understand language in novel ways and ways that can be used in particular in the clinical settings. So let me go to pain, and what is interesting about pain is that seems to be conceptually a very elusive phenomenon. Wittgenstein, who's considered a great philosopher, came out with the best thing he came up with is saying that it's something, but it's not something, it's not nothing either. So, and Dennett, in fact, Daniel Dennett, who became famous with this paper, Why You Cannot Make a Computer That Feels Pain, he goes on and on about the impossibility for a machine to feel pain, but then he concludes that even then, if it was a machine designed to feel pain, he would not kick it. And then, it's interesting that the International Association for the Study of Pain considers that pain is always subjective, which is it's true. But too often this is conflated with the impossibility of measuring, right? So for some reason, pain seems very subjective for us, whereas visual perception doesn't seem to be as subjective, but clearly they are, in my understanding, the same type of mechanism. So if we can measure anything in perception, we should be able to measure objectively pain, even though personally for us it's a subjective experience. And as you can see here, from your own reaction, pain has at least one function, that is to communicate a state. So in that sense, it's very intersubjective or objective, okay? So it is evident that we should be able to measure or say something meaningful in terms of pain, again, even though this is very subjective, as we know. So the other thing that is interesting is that when we started working on this, we didn't see any model. We didn't see anyone from physics and mathematics trying to bring some notion of analyticity to this problem, even though it's enormous. We all experience pain on a daily basis. Chronic pain is a huge problem that essentially has no cure. There is no treatment for it. It's a leading cause of depression, for instance. It's both from a scientific and from a clinical point of view, it's a really big issue. So the question is, can we model it? Okay. So I'll talk about trying to understand a model thermal pain perception in particular, trying to predict what is called now mind reading, and in fact Sergio was talking about that, mind reading in terms of trying to infer the internal state of the brain using fMRI in particular. And then I'll talk about a model for the dynamic components of perception, as you will see later what I mean by that. So we start with an experiment that our colleagues in the lab designed. So you have subjects that lie in the fMRI scanner with a thermal patch in the back, and you can control the temperature of that patch. So at 40 degrees is comfortable. At some point above 47, 48 degrees, it starts to become uncomfortable. And there is a way of rating the sensation, the perception of pain, that our colleagues worked on for many years, and is very consistent and is very well accepted. In this case, boils down to the subject relating their level of pain, which is moving their fingers, opening and closing the fingers. There are other ways of doing it, but the point is that it's very consistent for the same subject. It's consistent across subjects in the sense that we can rely on this measure of the level of perception. And as a control, I don't know if I'll talk too much about this. As a control, what we did was to, in the second experiment, encode the pain ratings in the height of a bar that is presented also in the scanner, and the subjects have to make a judgment as to the height of the bar, and that becomes a new rating. The whole idea with this is that one of the things that we wanted to see was whether the networks that are activated by this pain rating overlap with networks that are activated only for measurements, just measurement-specific networks that can be used for anything in the perceptual measurement, but don't have the emotional component of pain. That's the whole point of this control. So the results, when you do fMRI, and I know that Draulio is going to talk about the fMRI, I think, tomorrow. But just briefly, the idea with the fMRI is that you're measuring indirectly brain activity. It's not a direct measure, but it has the advantage that you can scan the entire brain. and has the disadvantage that it has a limited temporal resolution. Most cases about around 2 seconds of temporal resolution, and the spatial resolution is about 2 to 3 millimeters per side on what is called a voxel, the cube of resolution. But like I said, it has the advantage that you can do it in humans because it's not invasive, and you can see the entire brain. And if your task matches the time scale of the resolution, you have essentially very good data. That's the case here. The time scale is of the perception of pain is comparable. So there are things that, of course, we will never see with fMRI, but here you can see, like I said, the advantage is they can see the entire brain. So this is the type of traditional analysis that you will see in most papers with fMRI. So what you do here is correlate the expected response to a bout of increased temperature in the back with the response of this in the scanner for each voxel. And you see that there are areas that are activated during the pain rating, during visual rating, and there are some areas that are in contrast, that it's mostly the pain that activates those areas, so they seem to be pain specific. This is all very interesting, but from a more computational point of view, it's not that interesting. This is what people do on a daily basis, and in fact ignores, for instance, one thing that ignores is potential interactions between the areas or between the voxels, right? Because this is essentially a one-to-one mapping between the expected response and the voxel, and this univariate statistics. So when you want to go multivariate, things become a bit more complicated, because typically in the fMRI scanner you get resolution of about 30,000 voxels. So your dimensionality is 30,000, and if you want to do real statistics, you need a comparable order of magnitude of samples, but you cannot wait 30,000 times 2 seconds with someone in the scanner, right? So typically the number of samples is much more limited, so that impairs, or is a challenge for anything that is not univariate statistics. There are some ways around it. I hope I can talk a little bit about that. So the other thing that we found not really satisfying with this approach is that if you look at individual areas, so these are some of the individual areas that seem to be very much in play while you're perceiving this painful experience. And you can see that even though the temporal resolution is not great, there is a dynamics here. There is an intrinsic dynamic that is not uniform across the area. So there are certain delays. So that means that there are spatial temporal interactions that are part of the phenomenon. So for that, we decided to essentially do something similar to what Sergio was showing today regarding the mind reading experiments. And that is, if we have a good model of how pain and activity are related, we should be able to predict responses. And I wanted to dwell a little bit on this because in physics in particular, we don't pay too much attention to this problem, but in machine learning is a basic fact of life that if you're doing learning, if you're learning a model, you have to be careful in the way you treat the data. So this is really basic for any time that you see someone doing predictive modeling. What is very basic is that if you use the data here, let's say the first part of the experiment, to learn a model that will relate the activity of the voxels to the perception, to the actual perception reported by the subject, similar to what Sergio was showing today, using the activity to infer what the subject was looking at. You cannot use the data points that you use to learn in order to test. So you have to separate learning from testing. So if you use data in green to learn your model, to essentially fix the parameters of your possibly high-dimensional model, the data that you use to test whether your model is doing well or not cannot be the same, because you'll be cheating. And this is the idea that you can use to avoid the problem of overfitting that is very common in anything related to the brain, because the number of variables explodes very quickly. And like I said, in this case, we have at the very least 30,000. So this is an essential step that I think is very important for people coming from physics in particular to the world of neuroscience, that neuroscience, for the most part, has adopted this idea that if you learn a model, you have to be careful the way you treat how you test the model. And this is different from the idea of hypothesis testing. In hypothesis testing, typically, you assume Gaussian statistics. Essentially, what you're trying to see whether the two distributions corresponding to the two classes that you want to see, at least for classification, but it's similar for inference. They have well separated, and you essentially measure how big this distance compared to the standard deviation of the Gaussian variables. When you do prediction, your approach is very different, because you are going on a case-by-case basis. So when you test, you're not testing the population as here. You're taking one sample, one subject, and one particular experiment, and then you're trying to predict the exact, in this case, predict the exact shape of the response. So hypothesis testing and predictive modeling are very different. And in many ways, this is much more powerful, because you can do things like actually predicting, reconstructing the movie that you're watching, or predicting the exact response. Okay? So this is a little side comment, but I think this is very important to understand, because these techniques are creeping very quickly into neuroscience, and in fact, they're responsible for things like Google. Okay, this is what Google uses on a daily basis, on every millisecond of CPU time. Okay, so that's the setting for what we did. The problem still is that this is too big, and even in the simple case where you're saying is, well, I have my the voxels, right? The 30,000 voxels here, and I want to learn a model which is a matrix, or in this case, a one-dimensional matrix. Depends here how you encode it. That will allow me to predict the perception, and that should track over time, right? When I'm predicting, I should predict this, right? But as we saw, clearly there is a considerable amount of information in the temporal profile of the signal, at least when we looked at each individual area. So it makes sense to not include just the instantaneous value of a voxel, but the recent history of it, right? So even though we don't have a priori any information or any theory exactly how this is going to take place, but we know that the history of the brain is relevant, because even the single neuron is integrating over time. Now, like I said, if you start with 30,000 voxels here, now the dimension of this is n times 30,000. So there's not enough data in the world to compute this variable, right? So mathematically, essentially, it boils down to inverting this monster to compute the parameters. There is not enough data in the world to do this properly. This is heavily underdetermined problem. However, and let me wear my computer science machine learning hat and do some advertising. There is a technique that is very popular and everyone should know, because in computer science people use it every day because it works. It's called sparse regression. The idea with sparse regression is you can think of it as a generalization of something that perhaps you're more familiar with, which is the pseudo-inverse or the Moore-Penrose inverse. So here, all right, so if you want to solve this problem, one thing you want to do is invert these metrics to compute beta, but you cannot invert the matrix that is not square. To be square, you need 30,000 times n time points, right, to make it invertible. So Moore-Penrose gives the pseudo-inverse, which in MATLAB is p-inv, so probably you've run across it. The way you do that is of all the infinite matrices that will satisfy that the matrix times this is 1 with zeros, enough ones in the ones in the diagonal and padding with zeros. It gives you the matrix with the least norm 2. Okay. So there are ways of externalizing it and giving solving the problem of inverting X using other norms, not just norm 2. So ideally, what you want to do is minimize norm 0. You want to minimize the total number of regressors. Trying to bring it as close as possible to the number of independent samples that you have, that might not be possible, but at least that would be the best you can do. That is not analytic. Norm 1, so minimizing the norm 1, the sum of the absolute values of the elements, is analytic. And you can solve it as a simple optimization problem. It has a unique solution. So essentially what you do, you are trying to minimize, so forget about this for a moment. You try to minimize this error function, okay? Minimizing, instead of the norm 2, like Moore-Penrose, you minimize norm 1, okay? And that gives something that approaches what you would get if you were able to minimize norm 0. It has typically a very small number of non-zero elements, non-zero regressors, okay? And as you can imagine, that helps you significantly on avoiding overfitting, because if you are fitting parameters for which you don't have any data, that is what creates the instability associated with overfitting, right? So for the case of I'll show you here. We did this a variation of this, what is called elastic net, and it introduces a second parameter. So what is one parameter, which is the sparsity, so how much you want to contract and allow the norm 1 to be big or small. By adding norm 2, essentially, in the case of fMRI, you are allowing correlated voxels not to be thrown out. So norm 1 minimization, if you have a cluster of voxels, because it wants to be sparse, and they are correlated, it will take the best voxel and throw everyone else. So that typically is not very good, because at least in fMRI, things seem to be correlated in space, and that's good in terms of looking at intersubject variability or even intrasubject variability. But that's too technical. What is important to know is what happens when you apply this to real data. And so this is the result of applying this method to the problem of predicting from the fMRI data the actual perception of the subject, okay? And this is the correlation between the signal and the prediction. And this is what you get when you do Moore-Penrose or norm 2 constraint. And that's what typically you do, because, again, this is very easy to implement in MATLAB, for instance. But what we are showing here is the different curves that you get in terms of prediction depending on the sparsity parameter. Remember, here we have one parameter that is telling the system how many is pretty much how many voxels you allow. Okay, it's not the same as the threshold. It's not a threshold, because all you are saying is give me 100 voxels. I'm not telling you which ones. I'm not telling you which activity. They have to be the best 100. Okay, and you can see that you can get a very significant boost in terms of the prediction accuracy, going from the voxel activity to predicting the perception of a pain for the individual subject. And this is the case for the pain rating. Also for the visual rating, remember when they are tracking the height of a bar encoded from the pain experiment. Even when you subtract this and you do only what's called the pure pain voxels, you get a very, very high level of accuracy. And what's interesting is that it also allows you to see things that typically people don't report, don't see, because given that we can increase the dimensionality of the input without sacrificing in terms of overfitting, we can, like I showed, we can go back in time and consider the voxels up to 8 time points in the past. And now we see that there are areas that are active in the recent past that predict the level of activation of the level of pain perception with a few seconds delay. Okay, that's typically something that people do not report and report only what's called in this case, the red areas. There are areas that co-activate at the same window of time within 1 or 2 seconds with the pain level, the perceptual level. Now, so that right. So the red ones are the ones that are the voxels that allow you to predict the instantaneous perception, but the green ones are in the past. So they also, so when we build the model, we include, right? We include, so this is the perception of time t. We include the voxels at time t, t minus 1, t minus n. So those voxels that you see there are the regressors that have strong weight in t, or so zero delay, or in the recent past, right? So because given that we have this streak now, we can expand the dimensionality and still find meaningful weights predicting, like let's say here this is 3. So when the green dot means that at t minus 3, there is a significant weight that allows me to predict the perception at t0. But what is more interesting, and this is what things got for us very interesting, is that first of all, you saw already the variability. I didn't mention these are different subjects. So you see the different subjects have a different level of predictability. When you look at these are also different subjects for the same profile of stimulation. So this is the same stimulation, and you can see the huge variability across subjects. That's not all of it. This is where things get very interesting, that is for a physicist. So the thick line here, this is an very old experiment. The thick line here is the thermal activation, okay? So this one in the middle is similar to what we have here, right? And the thinner line is the response. Or is that, well, you can see, right? I don't know if you can see thick or not, but this is the response. But now what happens, look what happens when you add a little kink here, right? So you go from here to here, boop. It's a little change of 1 degree. Look at the response. It's more dramatic here. Same thing, it's just 1 degree, and look at the response. And this is consistent. This is very consistent. It's not random. So the response for the same subject will be also similar if you do just a little kink here. Okay? So that's the problem. How can you interpret without throwing up your hands the variability that you see here and the variability that you see here? Okay? So we thought we should come up with a model to understand that, and bypassing, at least initially, what's going on with fMRI, and try to understand this in a more theoretical way. So essentially, what we thought is, what is this pain signal doing, right? So it has to signal the threat of damage. That's a basic property. This is a thermal patch. So at some point, there is the risk of burning your skin. It could be good to anticipate threat, right? That we do that in many different settings. But it also needs to forget. So we need to forget pain. And sometimes it's very difficult to forget relationships. Are painful. Okay. So we thought that one way to conceptualize this signal that we see is by something that it has to satisfy this: signal, threat, anticipate, and forget. Okay. So we try to turn into elves now and come up with some magic. And this is the magic. It's just a simple second-order differential equation. So what is that this doing? So this is P is the pain, and there is the force that drives the pain, the acceleration of pain, and it's a threshold function, right? So there is some threshold upon which you really kick in with the pain. That might be close to the temperature for damage, or it might be lower. Okay. There is a damping component and there is a forgetting, okay? The same way that you have a damping in an oscillator. And there is a restoration component, right? That in principle, you can think of it like this. This will be the restoration part of the equation, but it also has a component that is proportional to the derivative of the temperature, okay? So this has both the function of anticipating the threat of damage, but also helping to restore the signal once the derivative becomes negative. And you can see this is a typical fitting of the real signal in green, in blue, with the predictive model for essentially we have 4 variables here. Okay, so there are, you can see only 4 here, but there are, there's 3, but there are 4 variables. So you have the 4 variables that define the subject, and this is the kind of fitting that we get with this relatively simple equation. And I'll show you the results, but of the prediction. But first, we need to know what is the new hypothesis against what are we going to compare how well the model is doing. And we thought of a couple of simple new hypotheses. One, that perception follows the temperature, which is kind of ridiculous, but it's a reasonable enough initial new hypothesis. Another one, that perception follows temperature only after you reach the threshold, right? So this is a linear model, and this is a linear threshold model. And the third new hypothesis is one in which you transform the second order equation into a first order equation, and essentially your system becomes a capacitor, right? And you can see that essentially by considering that this mu value is very high, so you can drop the second order term and you recover a first order differential equation. But as you can see, there are many features of the actual perceptual responses that cannot be captured by a first order differential equation. So this is a comparison of the prediction for the null hypothesis. So this is the R value for the null hypothesis, and this is the R value for our model. And these are different subjects. And the difference between the triangles and the circles is that the triangles correspond to okay, the circles correspond to this simple to the simple simulation. This is a square wave, and the triangles correspond to the complex one, where you have this little kink here that creates this seemingly crazy behavior. So we are significantly better than the new hypothesis, and we are better than the first order model, in particular for the complex stimulation. So when you stimulate, when you probe the system with the complex stimulus, the one that with the kink, is when you see the biggest difference between the second order model and the first order model. Okay. It's also true we took a completely different run, a different day. So we had the same subject on the second day, and we repeated the run, and it's not as better as the original one, but it's very good for the simple stimulus, and we have some outliers for the complex stimulus. The complex simulation, perhaps it's even, it's even more complex than just a second-order equation. And we also did what, again, people typically do, which is assume that you have a unique set of parameters for the entire population. So here what we're doing is fitting the parameters for each subject. Now, if you take the average and try to go back to each individual subject and predict it, you still do reasonably well for the simple stimulus, but you do really bad for the complex stimulus. So the complex stimulus really reveals what is unique about each individual in the way they are integrating and they're forgetting. One of the parameters is the time constant for forgetting. So you cannot lump everyone together. Each subject has its own individual set of parameters, including that and, of course, the threshold. So we have one of the parameters is the threshold. The complex stimulus is very simple. So the simple one is a square wave. There's a ramp here, but it's a small ramp. The complex one is either something like this or something like this. Just adding this little kink here. That again, it's just a 1 degree difference. Right? That's enough to trigger this mechanism of anticipating potential threat, because even if the threshold, right, that's what happens. No, we see that even if for this subject the threshold is here. So if you do this, the subject does not report anything. But if you do this, the subject reports something like this, because in a way this is predicting that you're very close to cross the threshold, right? Or similar here, right, if you do this. So here the perception goes very low because you are anticipating that the threat is going away, okay? So that's the whole difference between the two models, and that's enough to create this very rich behavior. Okay, so so one way, I mean, this is pure speculation, but another way to think about this particular model is that if you integrate the differential equation, you end up with these 2 terms. And you can think of it as a term that is trying to keep perception similar to temperature on average. And you have here a phase locking term. So even, I mean, your average can have a long time constant and average out to 0 here, and still have these phase differences, right? So this is positive, negative, negative, positive, and you average out, and on average, the perception is tracking temperature, but this term will try to push the signal to be phase locked with the inputs. Again, this is purely speculative, but that's one way we thought one can think about why you have these terms. Different from what we initially thought, that the idea of signaling and forgetting and anticipating. So there is work now. Some people are trying to recast this as predictive modeling or by the brain. So the brain is trying to predict. It's more in terms of machine learning and not in terms of differential equations that we thought. So this is interesting. I think in terms of potential applications, we thought that we might be able to combine what we learned from the inference from the signal to perception and what we learned from this model of behavior, essentially the bypassing completely the brain. If we can combine them, right? So we use what we learned about the model to get an even better mind reading system, right? So going from fMRI to the signal using the equation. So essentially what we do is we learn, initially we'll learn a model from the volt signal to pen rating. We learn how to combine with the temperature. And we have the model, the differential equation model. And then what we do is take just the volt signal, right, in the testing setting. We take the volt signal, we infer the temperature as opposed to infer the pain rating directly. That's what we were doing before. We apply the equation to the temperature, right? So here, all we need is the temperature. The parameters for the subject we learned. All we need is the temperature. Right. And then we predict from the temperature using the equation, we predict the pen rating. And we get a significant boost in predictability. And these mind reading experiments, we go from fMRI to the perception, because in a way, we are using a priori information about what we expect the perceptual signal to be. We are sort of regularizing the response based on a priori, what we learn about what to expect from behavior. Okay, so let me switch to, let's go back to the beginning and the idea of quantifying perception and in particular using the availability of behavioral and perceptual data out there. And this is relevant for this problem, and I will have to give you a disclaimer. I'm not an expert in music. I'll talk about the work that we did with a student in Buenos Aires, in fact, who's a musician, but is also a computer scientist. So I'll try to field questions about music, but I'm not a musician. But I was very interested in this problem. And of course, many people are interested in is to understand what determines music perception. And in the field of musicology, there are these ideas that are related to early 1900s Gestalt ideas, in particular the idea of good continuation, that is very powerful in terms of vision, that when Sergio referred a little bit to that, right, when we see something like this, we have a very strong perception of seeing a triangle, even when we increase the gap, right? So this is a typical Gestalt perceptual phenomenon. So essentially, good continuation means that we assume that there is a line here. Even though we know it's not there, and we don't see it, but we perceive this very strongly as a triangle. So these ideas have been transferred to music, and the basic essential idea is that one of the biggest determiners of music perception is the continuity of two consecutive intervals, 3 semitones. Okay. and I'll come back to this. So there is a good amount of work along these lines. In typical way, you do psychophysics, small samples with some small number of subjects, and a lot of introspection in terms of intuition of what people feel about perceiving music. So the question is, are these ideas really universal? Are they implicit in the data? And can we extract something similar to what people have speculated on a theoretical background? So these are some of these. I'll return to this. But what I wanted to say is that these ideas can be expressed very clearly in analytic terms. And to understand it, let's look at, this is Happy Birthday. Da, 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 da. Okay? And in English, right, it's C, C, D, C, A, E. Which is do, re, okay? So these notes are extracted from the chromatic circle. So these are the semitones. So if you know music, you understand much better than me what this means. But perceptually, we understand what it means. So you can encode this idea of 2 consecutive intervals being very relevant for perception in this way. So if we go to the chromatic circle, the difference between C and C is 0, between C and D is 2, between D and C is -2, phi 1, okay? So you can encode that as pairs for consecutive, for the 2 consecutive intervals. So one interval is 0, 2, 2 minus 2, -2, phi 1. And now you have a matrix of interval changes that encodes, it's a reduced representation of Happy Birthday. And so now we go back to what is the qualitative theory, and there are these 5 principles, and you can, there are ways of explaining some of them. The simplest one is perhaps this one, the registral direction. So small implicative interval is the first interval, okay? Imply realized intervals in the same direction, so the next interval is in the same direction. So if you're going, let's say, clockwise on the chromatic circle, you keep going clockwise. But if the first one is large enough, you go in the different direction, okay? And that's what is represented here, okay? So this is the first one, and this is down is positive. So if it's, and this is the second. If it's small enough, the second one will be in the same direction. If it's above 6, then you switch and you go in the different direction, right? So you're going like this, and then you go back. So this is a typical, so that's the way the qualitative theory works, is this is a typical expectation that you have. And it's one of them. And there are other ones that are a bit less easy to interpret. But in a way, this is the basic, the eigenfunctions, let's call them, that span basic perception, right? On top of it, you have emotional modulation, but they are, according to the theory, they are determined by these 5 eigenvectors, right? The problem with this is that this is all, again, very qualitative. So this is what we did. So we, and that's when we can use the power of the web and like I said, the availability of data that even 10 years ago was unthinkable. So there are many different databases. PitchNote is one of them that has the scores of close to 1 million different musical pieces spanning almost 3 centuries. So you can go back to Bach very easily, and goes to the early 1900s. And they provide you precisely these statistics, okay? But by year. So this is the statistics for 1763, for 1810, and for 1865. Okay. So the question is, what can we say about this? So the first thing we want to ask is, how good are 3 nodes on 2 intervals to, for instance, perhaps discriminate between these 2 guys, or at least between the time they lived. So the first thing that we did is apply a simple technique in machine learning. So I'll mention very superficially what it is. In fact, it's very simple. So when you have high dimensional data, so here our matrices are 12 by plus 12 minus 12, so it's 24 times 24 is the size of our data points. So when you have high dimensional data like this, you can use what is called KNN clustering to see how well you can predict labels of your data. And the idea is very simple. So in your high dimensional space, your points presumably will live like this, where this is one class and this is the other. And these are the points that you use for training. And then when you get the sample, right, what you say is, well, who are my neighbors? Let's say my first 3 neighbors, in which case it will be a 3NN clustering, and then for nearest neighbor. And then I use some definition of distance, which can be Euclidean or any one that you consider useful. So your 3 neighbors are 2 level X and 1 level O, so I'm an X. Okay, and that's it. That's all there is. And it has many advantages. It's extremely fast. It's the fastest method. It has disadvantages because it's very dependent on the local topology of the data, but that's besides the point. So what we did was ask for 4 clusters and learn the labels for clusters, and then classify and see how well we classify the years based on these clusters. Okay, so what you have here is the accuracy of the year being predicted by the same cluster. Okay, and as you can see, the clustering per year has this very clear structure. And then when you go to what musicologists, so this we took, in fact, you can go to Wikipedia, what musicologists consider the transition between Baroque and classical, between classical and romantic, between romantic and 21st century, these are the years that are considered the transition years. And you can see that the matching between the clusters and the periods is very good. The way this is done is they shoot up to 1, okay? So essentially, what we are seeing is, first of all, how well each cluster is, how well the clusterization is taking place, but also how consistent across time it is, right? That was what for us was surprising, that based on just this very simple procedure, we can essentially find an arrow of time in the scores, okay? But what we thought more interesting, because here we don't know exactly what we are learning, is we want to see if we can recover the principles or something like the principles from the qualitative theory. So for that, we do something, another trick from machine learning, which is non-negative metric factorization. So probably you're familiar, you should be familiar with singular value decomposition. So if I have data that I want to express as a product of matrices, which in you want consider the basis and the other the coordinates. If you minimize this subject to the norm of W equal to 1 and the norm of H equal to 1, what you recover is singular value decomposition. So you're orthogonalizing your data and you're finding the eigenfunctions, and then you see if with a few eigenfunctions you can explain well the data. NMF, non-negative metric factorization, essentially is the same, but subject to okay. So now you constrain the components and the coordinates to be positive. And that makes sense in particular when this is positive. And here we are computing statistics, so that's by definition our data is positive. Well, at some level, yes. In fact, NMF, SVD, KNN, they are considered just a family, and there is a large family of functions that can be considered a variation of this, where you just change the constraints. But kernels, I mean, you can apply kernels in SVM, and SVM is not really mapped to this. It's not mappable to this. But yeah, I mean, there is a large class, and this is also, orthogonal NMF, and there's a huge. Every computer science PhD student has his or her own method, so it's just a large number. But so this is very useful in many situations, in particular when your data is something like a probability and you want to, it doesn't make really sense to do SVD because then you have to interpret the components as negative probabilities, okay? So for us, this was very helpful. And this is what you get. So what we are seeing here is the component. So think of it as a eigenfunction or one SVD component. And this is the projection. So we see the same thing for these four components. We see how the weight is changing with the transitions, similar to what KNN finds, that are related to what are considered to be the transition between the big styles, Baroque, Classical, and Romantic. This is a background, right? So this doesn't have a trend over time, but these other four, they do. And as you can see, there are some similarities, but there are also very clear differences between what we recover and the classical factors, like the register direction. The difference is that with this, we can explain only 23% of the variance, and with this, with 5, we can explain 98% of the variance. So we think that these definitely are not final, because clearly depends on how good your data set is and how you separate, how you present the data to the algorithm. But this is one way of thinking how you have to do experimental psychology, and particularly musicology, and eventually go back to, ideally, you would like to go back to the lab, and instead of testing individual subjects with this kind of factor, you want to test them with the factors that you derive from this approach. Okay, so I'll talk about the last piece of work, and Diego, you can interject any time you want, because Diego is co-author. He's the expert in chess. And again, I'm not an expert in music or an expert in chess. I play chess, yes, but that's it. So the idea here is that, again, going back to the motivation is, and the way we are somehow increasing in cognitive complexity, we are interested in doing the thermodynamics of cognition, and in particular, on decision making. So, in fact, there is a large amount of work in terms of characterizing decision making as a physical process. And by decision making, most of the time when people talk about experiments, they're talking about binary decision making. For instance, a monkey deciding to foveate to a point in the screen or not. And in the case of binary decision making, people have tried to formalize it using a very simple model of diffusion. So essentially, you model your current state of belief in a certain decision as a variable that is diffusing in a one-dimensional interval. And you have a decision boundary or two decision boundaries. And reaching the decision boundary is equivalent to making a decision, because your evidence that you have accumulated somehow noisily reaches the optimal threshold for decision. So in the case of binary decision making, like I showed the case of the decision that the monkey has to make to foveate or not, this works very well. So as many physicists will recognize this as a first time passage problem. Right? So estimating the distribution of the intervals the time interval that it takes you to reach the boundary. Now, the problem is that for something like chess, or problems where there is more than one or two, essentially two decisions to make, this model seems to fall apart. And we came across this because we wanted to, we've been working with Diego and Mariano, who unfortunately is not here, on utilizing, again, the power of the internet, because now there are databases, online databases of entire chess games played by thousands and thousands of players, and involving millions of games and several hundred millions of moves per game. That's, there are other databases similar to that, but in terms of chess, you have the unique opportunity of combining a large amount of information regarding decision making in a complex environment. And in particular, in this case, the model of how you reach the decision and the distribution of time intervals to make the decision doesn't really follow a simple linear one-dimensional diffusion model. I'll show you a little bit more about that later. So in order to model it, what we decided to do was to extend this framework of understanding how you reach the decision and the distribution of times to reach the decision in an interval, going to the first next generalization, which is a two-dimensional space that now is defined by a boundary that can be circular, doesn't really matter, it could be square, but we model it as circular. But now that two-dimensional decision space has entropic barriers. So as you walk here, the only force that is acting on you is noise. You can include a drift, so a bias towards one or the other doesn't really change the basic statistics. Here, the difference is that as you walk, you might encounter a reflective boundary. So you bounce back, and you keep going and diffusing. And obviously, is the more entropic barriers there are, the more difficult it is to reach the boundary. But you eventually reach it, unless it's completely blocked. So that's the basic model. It's a very simple generalization of the very well-studied diffusion interval model for decision making. So let me essentially, that's the whole idea. But let me explain you exactly what we are doing. So we have this, you can correct me now, Diego, because this keeps growing, right? So we have 70 million games, that we have more, right? Like 3.5 billion moves. And what we do is record the response time. So similar to the monkey foveating to a fixation point, what we have is the response time, the time it takes you to make the move, to make the next move. That's for us. The response time is the time it takes you to make a decision as to which move to make. And clearly, this is no longer binary. It has a very high dimension, because you have to decide which piece and which move for that piece. And what we have is games that are constrained in time. So you have 3 minutes and 5 minutes games. That really is very interesting, because it adds a temporal constraint to the decision making. So you're really forced to make a decision, but still your decision is very high dimensional. Okay? So this, for the physicists, is not new. Essentially, we model it as a simple diffusion process with Gaussian noise that you can extend to a distribution, a differential equation for the distribution of probabilities, and solve the problem of finding the first passage time. In a few cases, analytically. In many cases, including our case, you can only do limiting distributions, so you cannot solve it analytically. No, or at least we didn't find a way of solving it analytically. But what is interesting is that in the case of an interval with one absorbing boundary and one reflecting boundary, what you have is a Poisson distribution, right? A semi-log. In semi-log, this is how it looks like. In the case that you have one boundary goes to infinity, what you have is a power law. And what we find is that this is typically how people have modeled this in terms of binary decisions, right? As a closed interval with one reflecting boundary and one absorbing boundary. It doesn't work for our case. Like I said, the only thing that we can do is, in order to get some analytic results, is model this problem as having one absorbing boundary where you cross the threshold and branches that go into infinity. And you can compute the tail, the tail of the distribution like this. But even that doesn't work very well, so essentially we have to resort to simulations. So this is the actual data. So this is the time during the game. And this is the distribution over the entire data set of response times, okay? So this is, here, this is a cut at around here. So this is how this distribution looks like. And you can see that an exponential doesn't fit. In fact, doesn't fit, it barely fits here, it doesn't fit the initial part of the distribution, and of course doesn't fit the tail. So here what we have is in black, the distribution at half of the game, and on top of it there is our fit, and you can barely discriminate the fit from the actual data. To give you an idea, this is the best fit that you get with a simple one-dimensional interval, right? That works for binary decisions. This is a fit with the comb model for a stretch of the distribution, but again, it only works for one part of it, whereas our model essentially fits the entire distribution. And this gives you an idea of the p-values for the comparison between the two distributions ridiculously low for the most part, except for the very, very end of the game. So here the p-value fails, but at just when you're reaching the end of the game. You can extract very interesting conclusions from applying this model that you cannot otherwise. So in particular, we separated strong players from good players, good players from bad players. And you can do that because everyone that plays in this system has a rating. And rating is very consistent. It's something that's interesting. It's really very consistent. It's a good predictor of the outcome of games, for instance. So what we have here is for the fit for each individual player, we have two parameters. One is the density for the individual player and for the time in the game, the density of obstacles or entropic barriers and the speed at which they are traversing each iteration in the game. So it's interesting that for the so this is time played in the game, and this is the mean for the distribution of obstacle ratios. This is one of the parameters for the good players and for the bad players. And you can see that for the good players, and in particular around the middle of the game, they in this model they are exploring a more complex space. So they are exploring a space with more obstacles, more entropic space, but they are doing it at a faster clip, right? So this is the distribution of time per iteration corresponding to strong players and weak players. So, and the time of iteration is constant throughout the game, whereas the obstacle ratio is not. So the obstacle ratio we fit for each instant of the game, for each part of the game. The time per iteration is fixed per subject, and you can see that the strong players tend to do faster exploration of a more complex space, which in fact we got some reviews. Well, one review saying that this was counterintuitive and therefore it was wrong. And we generalized this to a very different domain, and that is the domain of people browsing a shopping website. This is Mercado Libre in Argentina. And we get also very, very extremely good fit for the distribution. This is for the ensemble, not for individuals. We also check that we can, in fact, fit individuals very well. Well, again, you're browsing, and not that the decision implies buying necessarily, but it's not buying, time to buying, but time to the next click. In the context of buying, it's similar to the chess game in that sense that eventually you buy, but you're clicking, right, and making the decision of what to click or not to click. Now, this is very much speculation, it's pure speculation, but one of the motivations that we have is, why use chess? Well, chess is very complex, but also is very well characterized, and it's something where it's a task where the performance of man and machine is comparable. Okay, that's I think what I find particularly interesting about chess is that even though in my case my smartphone kills me, there are professional players who can compete with the best machines there are. So that, for me, is saying that there might be some underlying mechanism that is similar, both man and machine. Again, this is pure speculation, but what is interesting is that there are the proofs that chess, or a generalization of chess, is a hard problem in the sense that it's similar to an MP problem, that the only way we know how to solve at the moment is by doing exploration and search and delete. So we search on the tree, and if we go to a dead end, we come back and we search again. So that is what we try to capture in the model, right? We could have done it on a tree, but it doesn't matter. It will not change very much the results. What is interesting is that you can take an archetypical MP problem, like the traveling salesman problem, and apply the algorithms that are currently used to solve it, and look at it in the same way, look at it as experimental psychologists would do, measuring the response time to the best possible solution. And the response times that you get in simulations can be fit very well to a confit, the confit that we use to fit parts of the distribution of response time. So this is what we are thinking now, is it might be possible to find some common ground between the way we play chess beyond all the additions in terms of how much you learn, how much you play, and all the strategies. At the end of the day, and in particular in something like speed chess, 3 minutes, 5 minutes, at the end of the day, what you are doing is not different from what the computer is doing, which is exploring a complex space almost at random and trying to look for the best response and come back and do it again. And in fact, we have a limited number of computers playing. And when we look at the statistics, they tend to be faster than humans, but in terms of the shape of the response, it's very similar. We are trying to get more statistics comparable to the ones we have for humans to see if we can fit the same model. And I think, okay, I'll skip language because someone else will talk about it and it's time. So I'll stop here.
We have time for 5 minutes of, a couple of questions. Don't be shy.
All right. Can you go back a few slides to that slide where you have the drift diffusion model versus the multidimensional? Oh, there it is.
Yeah.
So this model, it's close to some kind of percolation problem. Do you know of other examples in neuroscience in general where this kind of approach can be taken or something like that?
Not that I know of in terms of actual percolation. Oh, well, I mean, to some extent, this idea, there's few spikes that propagate through a large network that Abeles proposed, has some flavor to that, but I don't know of anything like, computing statistics and fitting. And I mean, metaphorically, that sounds a little bit like that, right? What Abeles was saying, that just there's only a few spikes that count and they sort of percolate through some cascade mechanism. But there's nothing that you can really measure in any meaningful way. Beyond that, I don't know. And in fact, I mean, it's surprising that the literature on decision making based on diffusion of one interval is overwhelming. This is what everyone does. It's surprising that clearly, I mean, going to 2D without obstacle doesn't make any difference. I mean, it changes a little bit the scaling, but that's it.
The analysis you did for music, you did for Western music,
Yes.
which is quantized. How do you go about Eastern music?
Well, we've been banging our head against the wall with that. There are some databases, but it's only now coming on online. Yeah, it's a completely different world. And in fact, we are doing similar things with language, and you have the problem that, in Romance languages and in English, we have at most, English has 70,000 different words. Spanish and Portuguese are 30,000. They have 520,000 in China. So everything is much more complex, even with music. Yeah.
Do you suppose that you could come up with a single module that works both with Western and Eastern music? Because that would be the
that
desirable,
would be
right?
interesting. I don't, as little as I know about Western music, I know much less about Chinese music. Yeah, it's very different. Yes. Yes. What I know about Indian music from a colleague who plays, it sounds very different. But I don't know. Maybe deep down. Okay. Well, there were several questions. I think that. Okay.